Good day, Math 30-1s. Today we're going to do a little bit of magic as we prove identities. We are going to be looking at a lot of our Pythagorean identities, double angle identities, sum and difference formulas, and really learn how to apply these to not just verify, but do something called prove. Now, in math, proving is a very, very powerful statement. When someone proved that a squared plus b squared equals c squared, it allowed a lot of possible going forward in mathematics and in physics and in many applications of it. The first thing to chat about when we talk about proving identities is a potential problem. I'm going to work through just a very quick investigation, and I'll comment on sort of an issue that could happen. Let's start with two facts. An a and a b. Let's just say these are two non-zero quantities. For example, I could say that a is 3 and b is 3. Let's say they are non-zero but equal. I should therefore be able to say if they equal, this is a balanced equation, and I could multiply both sides by a. A times a times b. I could subtract both sides by a b squared. I could factor both sides as a difference of squares, and a greatest common factor b comes out. I could look at the two terms here, and say, hey, this a minus b matches. Let's divide both sides by a minus b. We're left with an a plus b that equals b. And all of a sudden, if a and b are the same thing, I could say that a is b, and that b plus b is b, that 2b is b, and 2 is 1. All of a sudden I started with something that was true and ended up with something that we might sort of say I don't really understand how 2 is 1. Well, there is a mistake that occurred in here, an assumption of sorts. And it's challenging to try to think about it unless you are being very, very, very intuitive of the fact that a and b are the same thing. What is a minus b? 3 minus 3, 4 minus 4, 5 minus 5. I'm technically dividing by 0 there, and I'm dividing by 0. If we're dividing by 0, that is something that we're not technically allowed to do, so all of a sudden all of this isn't actually possible. There is a risk when we are proving, when we are doing operations, that maybe assumptions can get created. We saw this kind of scenario once earlier, in a radicals unit, where I could start with something that is technically never true. The square root of x can never be a negative number. Square root of 4 is 2. Square root of 1 is 1. But imagine if I were to square both sides. We end up with x that equals positive 1, something that could be true. When I squared both sides, we resulted in a bit of an ambiguity or an ambiguous statement of what it was. If I were to say x is 1, and I were to say I just square rooted something, you could say that, well, maybe this was a negative 1, maybe it was a positive 1 that got squared. We don't know the history. We create ambiguity when we square. We create a potential dangerous scenario when we divide both sides by something. So what we're talking about today is this danger in math operations when we square both sides, when we divide both sides by a number. And so what we're going to do is we're going to try to avoid all this danger in math. And so when we're proving, we're going to express each side of the equation as equivalent. We're going to say this side equals this side, and we're going to try to get everything to match. We're going to try to prove. Now, one or both sides of the equation must be manipulated without affecting the other side so that they may match. We're going to work on one side only and not touch the other side. It's deep. It's deep. So, again, a choice of verbs. Verify versus prove. Verify, we talked about last day. Apologies. Verify, we said, is where you sort of inductively plug in one number to see if something is true. So in an example like this below, I could say verify for a value of x to see if it's true. So arbitrarily, I'm going to try I'm going to try x equals 45 degrees. 1 minus sine of 45 degrees, which we can square, sine of 45 degrees, cos of 45 degrees, cotangent of 45 degrees. There's a fist pump right there because we know that any tan and cotangent of 45, it's always a 1, so that one's easy. 1 over root 2 squared. 1 over root 2, 1 over root 2, and we end up with 1 minus a half. Now 1 over root 2 times 1 over root 2 is a 1 over root 4, or a 1/2. I end up with something that is true. So I could say that inductively 45 degrees worked. Would 30 degrees work? Maybe. Let's try it, see if it works. In fact, it would. Maybe it's unique to 30, 45, and maybe even 60. What if 10 degrees were tried? What if it was 9.7 degrees? Verify is not a very powerful tool. Verify is trying one number at a time, see if it works. Prove is much more powerful. Prove is using deductive logic or facts to make broad statements. So I could say, all right, forget using 45 degrees. Let's just say that every angle would work. Let's say every possible angle would work. And how do we do that? Well, we might get to use our formula sheet and look for some of these facts. I see a 1 and a sine squared. I'm looking somewhere on my formula sheet for a 1 and a sine squared. And in fact, I see one up here. I can manipulate the first Pythagorean formula to say 1, subtract over a sine squared, and what's left is a cos squared. So sine squared plus cos squared is 1. Subtract over the sine squared, and we can say cos squared is 1 minus sine squared. So in fact, on the left side here, I can swap this out with cos squared. Now, you might be thinking, you know what? I see a cos squared on one side, I see a cos on the other. Let's cross those off. Now, in fact, we're not going to be allowed to do that anymore in proving. We're going to have to draw a dotted line down the middle and say, you know what? I'm going to need to only work on one side at a time. One or both sides of the equation must be manipulated without affecting the other side. We run into these dangers when we divide both sides, or we square both sides, or we do something to both sides. So when we prove, we're going to draw a dotted line down the middle and say, can't cross. Thou shalt not pass. So we're not going to be able to divide both sides by cos, because then we're saying there may be restrictions that create assumptions. Instead, we get to maybe turn this cotangent into a cos over a sine of x. In fact, sines could cancel, and what we're left with is a cos times a cos, and all of a sudden, the left side says cos squared, the right side says cos squared, and I have just in fact proved that the left side is the right side. You can represent a proof being completed with a little tiny box as a symbol signifying the end of a proof, or you can use QED, which I think stands for Quantum Educatum Destratum, or something like that, Latin to say educationally demonstrated some proof. So this is what proofs start to look like. Dotted line down the middle to say do not cross, work on one side or both sides independently and make them say the same thing. All we're going to talk about in the proofs day today are strategies. So questions are going to get much more complex. They are going to get much more complex, but basically seeing strategies is what's going to make this possible. So sometimes changing double angles into single angles can help. So when we look at something like tan of x and then a 1 minus cos double angle 2x over cos of 2x, we're maybe trying to work on the more complex side first. It's pretty tough to take a tan and change it into this stuff. I can say, well, tan is a sine over cos, but I'm sort of limited in what I want to do there. Right side, I can say, well, I see some double angles. I see a single angle on the left. Let's swap out these double angles. Now you might say, well, how do I swap out cos of 2x? On my formula sheet, because you're already comfortable, you recognize there is 1, 2, 3 cos double angle formulas. 1, 2, 3, and they're all different. So how do we know which one to choose? We don't. Sometimes you have to take a 33% guess and see if it works out. Sometimes, though, there's a little bit of foresight. Sine of 2x doesn't have a lot of choice. All there is a 2 sine cos. And now it's not going to be a 33% guess in this one, because we can say with a little bit of logic, you know what? What if I don't see a 1 plus or a 1 minus, or I don't see an extra number hanging out on the left side, I just see tan of x. How am I going to get rid of that 1? How am I going to get rid of that 1? On the formula sheet, one of these choices for cosine has a bunch of 1s in it. Let's try to get rid of that 1. Which choice would get rid of that 1? If we use this one, 2 cos squared minus 1, 2 cos squared minus 1, there's going to be a negative, because we're subtracting this whole thing. The negative is going to affect everything in there, and the 2 cos squared minus 1 will eventually become a positive 1, making it a 1 plus 1, a 2 plus a 2 cos squared. And that might not be what we want. And you can try it and see if it works, and sometimes that's what you have to do in a proof, is try it, see if it works. I'm going to alternatively select 1 minus 2 sine squared to say, you know what, I'm going to get rid of that 1 confidently with a 1 minus a 1. I'm going to get rid of it for sure. So now I can say 1 minus 1 plus 2 sine squared of x, all over a 2 sine x cos x. The 1 minus the 1 cancel, and we're left with a 2 sine squared. I wrote 2 sine squared as 2 sine sine, just so that we can see the canceling a little bit more clearly. And in fact, the 2's cancel, the sines cancel, and what we're left with is a sine over a cos. I ran out of room. A sine over a cos, which is in fact a tan. The second that I can make both sides match, sine over cos, little tiny box. And again, you start to have a little bit of foresight, but you might not be there yet. So there's one you could try, which is very, very similar, and you know you have the answer if both sides match. But we're going to try some new strategies. Sometimes rationalizing can help. When I look at the two sides and I draw my vertical dotted line to say thou shalt not pass, I don't really see any Pythagorean formulas. It's not a 1 minus cos squared. It's not a 1 plus a, well, that's not anything anyways. And I can't cross multiply to say sine squared and a 1 minus a cos squared. So what do? We create formulas where they don't initially exist. I'm going to work on the right side for a moment, and I'm going to intentionally multiply the bottom by its conjugate. And you'll start to see why this strategy is interesting. You would say, well, I would never think to do that. That's why we're showing strategies. On the very, very right side bottom, we have a conjugate pair, which means when you multiply them together, the middle terms should cancel. We do have a 1 times a 1, a negative cos and a positive cos, of course, cancel out, and the last connection is the negative cos squared. And now I see a 1 minus cos squared, which we're going to say, hey, that's a sine squared. We'll swap that out in a moment. I'm intentionally going to leave out this sine of x and not put it together because what I see on the left side, I'm keeping this in mind, is a 1 minus cos of x. 1 minus cos of x. I don't want to mess this up because I need to have it by itself. So I'm going to swap out this bottom 1 minus cos squared with a sine squared. And as you see, the sine of x cancels with one of those signs, and we're left with a 1 minus cos of x over a sine of x. Little tiny box. So rationalizing is a way sometimes of creating identities or helpful scenarios that didn't exist moments ago. 2 more strategies in our proving lesson before we get to apply some. Common denominators can sometimes help. If ever you're dealing with a scenario where there might be fractions, common denominators can be a great option. So secant is actually a 1 over cos of x. I'm going to be clear, that's the big division right there in the middle. That's the big division. Tan is a sine over cos. A cotangent is a cos over a sine. When I say get common denominators, I'm talking about this section right here. Cos, sine. Those are very different denominators, as different as a 2 and a 3. Cosine, let's put a sine of x and a sine of x to make this say sine cos. Now this denominator needs to say sine cos. Thou shalt not pass. I violated that one there. So now the bottom says sine cos, and we can write the top again as 1 over cos, dividing by sine times sine, plus cos times cos, all divided by sine x cos x, to which you look at and say, sine squared plus cos squared, that looks familiar. What is sine squared plus cos squared? 1. So I get to replace this entire part right here with a 1. At the same time, I'm going to use the strategy I've employed in different lessons to say, as we divide the fractions, our denominators shift, and we end up with a sine of x, cos of x on the top, a cos of x times this 1 on the bottom. Those cancel. We're left with a sine of x, little tiny box. Again, proofs can be very motivating when they go well and super frustrating when we have no idea. Practice is going to be crucial for today. Sometimes factoring can also help. Often questions you'll look at initially and you'll say, I have no idea what to do. No idea. Sometimes changing double angles to single angles is helpful. Sometimes changing cosecants and cotangents and tangents to sines and coses help. So I'll maybe just start on the left side and say sometimes you can work on both sides. There's a cos over a sine is a cotangent. A cosecant is a 1 over sine. And now I can actually see the left side as what it truly is, as sines and coses, as cos x minus 1 over sine of x. I'm going to try to make that my goal. What do I see on the right side? I see a sine of 2x. I see a sine of x. I see x is on the left, so maybe we'll say let's get rid of these double angles. Not a lot of choice on the bottom with swapping out a sine of 2x, so I'll start there and say sine of 2x is a 2 sine x cos x plus a sine of x. The top, there's a little bit of choice. What are we going to swap out this cos of 2x with? Well, our choices. We could say cos squared minus sine squared, cos squared minus sine squared minus cos. Maybe that helps. It's something you could try. Is 2 cos squared minus 1 going to help? 2 cos squared minus 1 minus cos. Well, they're all cosines. 1 minus 2 sine squared, a 1. There's going to be a 2 sine squared minus cos. Sines and coses, maybe like the bottom. Well, I'm going to share that you can actually, again, try one, see if it works. Sometimes more than one will actually work. If you do use 2 cos squared minus 1 and keep everything as cosines, you can actually factor using luckier decomposition, however you factor, to make this look a little bit more like a grade 10, I should rewrite this, minus a cos of x minus a 1. This looks very much like 2m squared minus m minus 1. We've been factoring trigonometric expressions for a little while. How do we factor this? Well, we try to determine what factors multiply to make things work out cleanly. A 2m plus 1 and an m minus 1 looks pretty nice. The very, very bottom, I'll rewrite just once, but we are going to factor this in just a moment. Not as a lucky decomp, but as a greatest common factor, sine of x can come out. So the top factors nicely as a 2 cos x plus 1, the bottom factors as a cos of x minus 1, and the bottom has a sine of x that can be factored out. What you're left with is a 2 cos of x plus 1, which kind of makes sense that there's a 2 cos x plus 1 on the top. 2 cos x plus 1, 2 cos x plus 1. Many people are going to make mistakes in how they cancel fractions. Like, some people might look up top and say, there's a cos squared, there's a cos, and you try to cancel those out. But there's danger in canceling during addition. Imagine if I said, what is 1 plus 3 divided by 3? To which you would say 4 divided by 3, or 1 plus 1. This kind of canceling doesn't really work. So be careful when you're canceling that you're only canceling when there's a multiplication that's occurring. Those cancel. What you're left with is a cos of x minus 1 over a sine of x. Little tiny box. Common denominators. Factoring. Occasionally rationalizing. And a lot of swapping out from your formula sheet is crucial. I wish you good luck as you practice proving.